So last time QuickTime crashed, so I didn't have a video. I guess I won't go to full screen mode, and we can keep our eye and make sure that little stop button is still there, which unfortunately the screen recorder can just crash and not give you any indication that it crashed. So sorry. So our plan for today is random questions as usual. I'll make some remarks about homework. We'll continue talking about exact linear algebra. And the next two topics we'll talk about are graph theory and group theory. So the screen recorder started. First, general questions. Yes?
I noticed that homework 6 wasn't in our grades in that folder. You just said you haven't done that yet.
Oh, I did not run that step. Yeah. So I collected homework 7, I redistributed it for grading, and I created homework 8 and assigned it. But there's another step, which is to run a command that takes the graded homework 6 and pushes it out, and I realize I did not do that. So I'll run that command.
Thank you.
Yep. Yep. So thank you for the reminder. Any other questions or comments? Okay. So speaking of homework, so here, let me go over homework 8 very quickly. Homework 8 is the last homework assignment. There will be something due. So this is due on May 26th. There's something, namely your final project, due the following Monday. And then there's nothing else to do except for your grading of other people's final projects. So this is the last homework assignment that's due. It has one question, which is just a linear algebra calculation or two. And I think this should be, I mean, each of those two are like 2 lines of code, maybe 1 line of code, and some patience. And here are some group theory computations, which I will show you how to do some group theory computations more later in the week. And if you just do what I show you, then you'll be able to solve these. They're just completely straightforward exercises playing around with the functionality in Sage. And that's it. And then there's some graph theory computations, which involve making a lollipop graph and computing a few things about it. Again, a pretty straightforward exercise using Sage. And I'll show you how to do these sorts of things later this week. And then problem 4 is about your final project. And it's about organizing the presentations. So each of these questions, so one is what's the title and who is in your project? What format will you use for your project? Are you going to use PowerPoint, LaTeX Beamer, Sage Worksheet, your laptop, etc.? The presentations are going to be the last week of class. And I've created a file which you can click on. And as long as you're a collaborator on the shared project for the class, you'll be able to edit it. And what you should do is put your project along with who's involved in the project there. And by project, I mean your final project for the course, not Sage Math Cloud project. Does that make sense? And if you click on this file, sorry, let me command click on it. When it comes up, you'll see that it has, so the presentations are 5 minutes, and with 1 minute to switch from one person to or from one project to the next, that's 6 times 9, or like 30 seconds really to switch from one to the next. The maximum possible number of presentations in a day is 9. So what you'll do is you'll put your name and your project there, and if a day fills up, then choose a different day. So if you have any time constraints or preferences, you'll want to do this sooner rather than later. But of course, please don't cheat and just move people out of the way that have already put their names there. Because of course that's possible as well. On the other hand, if you look at this page and you haven't put anything there yet, and there's already 27 things there, then probably you won't get to percent. There might be a couple of people who don't get to percent just because there's not enough room. So we'll see. I'm hoping that there will in fact be less than, well, we'll see how many projects there are. I don't know at this point because there's several people working in groups. So we'll see. Yes? It will not affect it. Well, I don't want to say either way, but I may have to do something more one-on-one or something like that. Hopefully we won't have to do that. Also, if it comes to that, it's possible that I'll add the previous Friday for additional presentations. let's just see how this sizes up first, okay? So I could easily just add, Friday the week before. I prefer not to, but I could. Okay. And I've done these, so in a lot of Python conferences, they have lightning presentations, which are 5-minute talks like this. It's extremely common at PyCon, for example. They have a sequence of these. I've done them in probably 10 courses I've taught. And as long as you set up a timer that's automated, then it does actually work, and you can do 9 presentations in a day. You just start on time, and you stop the person instantly. Great. Wow.
I can't actually type on my phone.
Sorry. It's kind of fun watching this. Okay.
Should wait till everyone finishes.
Yeah. All right, so that's that. So that's the next homework assignment, and I think you'll find it fairly straightforward. I want you to put a lot of effort into your projects, which is why I'm not making this homework assignment very involved like some of the past homework assignments, okay? This should be, if you pay attention to class, it should be completely straightforward to do the 3 problems. It's just exercises so at least you try things out. All right, so now we're going to finish, or we're going to give the second part of our discussion about exact linear algebra, and I'll show you vector spaces, and then I'll talk about vector spaces over finite fields very briefly with the demo, and show you a little bit of coding theory, which if you've never seen it before is a pretty neat idea that involves vector spaces over finite fields, and is something that Sage is pretty strong at. And then we'll also talk about asymptotically fast algorithms for linear algebra, which is in itself a major interesting research area in mathematics, and it's a part of Sage for which we put an enormous amount of effort into implementation, implementing things that didn't exist anywhere else except Magma when we started, in many cases. Okay, so that's the setting. Oh, by the way, if you are interested in doing a lot of coding related to Sage, for the second 2 weeks of next month, we're having a Sage Days workshop. So this is just a workshop where we code on Sage all day long and all night long, possibly. And I've rented this house, which is in Portage Bay. So it's just like, right over by the, it's right over there, a few minutes away. And this is what it looks like inside. So there'll be a bunch of people from Europe staying there, and you can sit on the patio and code, fix bugs in Sage, whatever. Everybody here is certainly welcome to get involved. If you want to find out about more details as we organize them, go to wiki.sagemath.org, and it's under past and future workshops. These are Sage Days 58 and 59. There's also Sage EDU Days 6. If you're interested in issues involving undergraduate education, then you might be particularly interested in this one. It'll have quite a large number of people who teach at community colleges and so on. There'll be a lot of talks. They'll talk about their experiences with Sage, a lot of just open-ended discussions about technology and teaching. And so that's going to be in the Mechanical Engineering Building, the 16th through 18th. And then the rest of the time, these workshops, which are really it's just going to be one long workshop. The second 2 weeks of June will be in that house that I just showed you for the most part. Okay? So if it's like late in June, you're around, and you're like, geez, what should I do? Maybe I'll write some Sage code. Then just email me or whatever and come to hang out, and we'll be doing a lot with Sage during those days. Okay? All right, so now on to the lecture. Any questions before we get going on this? Okay. All right, so vector spaces. When I say those words, do they mean anything to you? Okay. Vector spaces. Remember that was I don't know if you remember them from 308 or whatever, but that was that thing where they had a definition and it was really long and it had like 8 axioms or something, and you're like, whatever. And then you see some examples and you're like, okay. So vector spaces are something you can compute with in Sage to some extent. And in Sage, they're pretty concrete objects. So like one of the ones you'll frequently see in a class is Rn. So here's, say, r to the 5. This is all five tuples of real numbers. So it's a vector space. here's Q3, so I'll let V be Q3, and that's a vector space of all 3 tuples of rational numbers. And you can also take some vectors and ask for their span, and that's another way of getting a vector space. So the code is for its span over Q of those 2 vectors constructs, those are actually lists, it turns them into vectors. It constructs the span of those 2 vectors. So it's like a plane in 3-dimensional space. But the neat thing about vector spaces in Sage is that all kinds of set theoretic operations and so on, you can just do them directly with these vector spaces. So you construct a vector space, and then you can construct another one, and if you do plus, it finds the sum of all vectors, one in one space, one in the other space. If you do v dot intersection w, it finds the vector space, which is the intersection of the 2. If you have a vector and you want to know if it's in a vector space, you can just use the in command. So you can do things in a language that's kind of like what the more abstract language of mathematics, but it's in the computer. And it comes up very naturally, these vector spaces, in the context of, say, remember when you have a matrix and you want to solve a system like ax equal to v, and you find a particular solution, but you want to find all the solutions, and there's often infinitely many. What you do is you find the null space of the matrix, and then you add any element of the null space to a particular solution to get an arbitrary, to get like all the solutions. And the null space of a matrix is an example of a vector space. So here's an example of that. So right kernel, again, there's the collection. If you have a matrix, then you can consider the collection of vectors, so that when you multiply the vector on the right by the matrix, you get 0. Or you could consider the collection of row vectors, so when you multiply with the matrix on the right and the vector on the left, you get 0. And so in Sage, there's right kernel and left kernel, which allow you to compute the kernel on either side. In most programs, what they would do is, if they gave you a kernel command at all, and I just want to remind you, kernel equals null space. Mathematicians call it the kernel, and linear algebra classes call it the null space, but they're the same thing. Kernel equals null space. So there's right kernel and left kernel. And if you only had one or the other, you'd have to use transpose. Yes?
I've been using the just m dot kernel.
Yes, that's going to be one or the other.
It doesn't.
It's probably the left one, which is probably not the one you want. But let's see. Look at the documentation. Returns the left kernel of this matrix. So it's the collection of vectors x, so that x times m is equal to 0. Maybe that's not what you wanted. In fact, everything you did with that was wrong. Sorry, unless your matrix was symmetric. So watch out. The reason for that, similar to, well, I mean, I explained this a bit last time, but when I started Sage, the main system I used was Magma, which is an Australian computer algebra system. And in the implementation of their system, everything, like kernels, everything is from the left. So the matrix is on the right and the vector's on the left. And I was really trying to build a similar system for my personal use at the beginning. And so my default was to do everything like that. And then other people came along who wanted to maybe teach in the United States. And so they added right kernel and left kernel to make things explicit. Okay, so that's kernel. And oh, as you can see, looking at the help, there's a lot. This doc string is extremely long. And the amount of code behind computing a kernel is enormous. So, okay, and if you have a vector space, by the way, so we just computed one as a kernel, it has a lot of methods. So if you do v.tab, you'll see there's an enormous number of methods. And I'll just tell you, well, addition table obviously isn't going to work, but one interesting method is the dimension, which is some quantity associated or a number associated to a vector space, which you may have had to deal with. There's a basis, etc. Here's another example of a vector space. I just computed another kernel and got another one-dimensional vector space. And now I can ask for their intersection. And I get 0. There are 2 one-dimensional vector spaces, so they're like 2 lines. And so unless they happen to be exactly the same, they intersect in the origin. And so their intersection is that 0-dimensional subspace, the origin. If you add them together, the sum is by definition the collection of all sums of something in one of the vector spaces plus something in the other. And the result is a vector space, and in this case has dimension 2, and there it is. And here's a basis for it. So these are really tiny examples, but this code will work even if things are much, much, much larger than this. Like the dimension could be several hundred, and it can deal with it pretty well. And you use things in the same way. And this is the rational field, but you can work over many other base fields or even rings. Everything works pretty well over Z, which is pretty subtle, and the algorithms are all kind of different than what's done here. And over other fields, things are pretty usable as well. It should work over general principal ideal domains. If you haven't taken abstract algebra, you won't know what that means. But things like polynomial rings over fields, but little has been implemented in practice. So in fact, a lot of things fall over in that case, even though they should work, because the algorithms are good enough, but they're not implemented fully. Okay, now linear algebra over finite fields. So next topic, and this is relevant to coding theory. So first, raise your hand if you know what a finite field is. Okay, cool. So like half of you don't. So I'll tell you what an example of a finite field is. There it is. Take the numbers 0, 1, 2, 3, 4, 5, and 6. There's 7 of them. If you have any two numbers, you can add them together and reduce it mod 7, and you get another number in there. If you have any two numbers in there, you can multiply them together and reduce mod 7, by which I mean divide by 7 and take the remainder. And you get another number in there. And the result in set of 7 things is a finite field. It's an example of a finite set where you can add and multiply any two elements. And moreover, you can divide any element by any other non-zero element. So, let F be this finite field. And if I take F2, I can divide it by F, 4. That's a non-zero element. And the result is going to be something in there. Does anybody know what it'll be? Maybe. He says 4. Any other ideas? So in order to figure that out, you need to figure out what, when you multiply it by 4, gives you 1. So what number?
52.
First, figure out what multiplied by 4 will give you 1, and then multiply that by 2. So, or you could do what you just said. But you're right. If you want to just directly use the definition, what when you multiply it by 4 gives you 2. That would also work. 4 does not work, does it?
Yeah, so 2 times 4 is 8, which is 117.
Ah, okay.
And hence double that is 4.
Woohoo. So the multiplicative inverse of 4 here is 2. So if you multiply 2 times 4, you get 8. If you divide by 7 and take the remainder, you get 1. And so now in order to compute the product f of 2 compute f of 2 over f of 4, you can think of it as f of 2 times the inverse of f of 4. Since 2 is the inverse of f of 4, you just multiply by that inverse. It means, so f of something means coerce or convert that something into the finite field f. So f of 2 it's something that in Sage it prints out as just 2. However, if you look at its parent, then it'll say finite field of size 7. So it's, yeah, if you think of f of 2 as an equivalence class, then 2 and 9 would both be in that equivalence class. 2 plus 7 times k for any k. Yeah, you can. One model of GF7 is the set of equivalence classes of integers modulo 7. But that's just one model of GF7. It's not the only way to view. It's not. It's false. It's not really right to say that the element 2 in GF7 is that equivalence class. It's just that if you take the set of equivalence classes of numbers mod 7, then you get an object which has a field structure, and that field's isomorphic to the one I just defined. But you could also think of GF7 as being the numbers, like the integers 0 through 6, but with a different addition and multiplication than you normally put on the integers. Or just two different ways of viewing it. So finite fields are just fields that are finite. It's like so a field is something closed under multiplication and division, etc. And finite means there's only finitely many elements in it. And for every prime number p, you have a finite field. But there's actually all kinds of interesting finite fields of cardinality any prime power. And it's actually pretty tricky to prove that for every prime power, there's a finite field with that cardinality. But you can construct those in Sage as well. For example, I'll say k equals gf9. And you have to give the generator of that field a name. So this is the finite field of order 9, or the up to isomorphism finite field of order 9. And those are its elements. So for every prime power, there's one of these objects called a finite field. You might think this seems ridiculously abstract, but finite fields are used an enormous amount in applications. They're probably one of the most applied things out there that is discrete. And they're especially old. I mean, they were developed a lot in the 60s by people doing encoding data in various places. Okay, so here's just a few examples of linear algebra involving a finite field. So you can solve systems. You can do everything just like you would do over the rational numbers. A cool thing, though, basically a big distinction between finite fields and the rational numbers is if you take a couple of rational numbers and start multiplying them together, you end up getting a really big rational number. If you take some elements of that finite field I just showed you and just start multiplying them together, things never get big. They just stay small, which is really nice. So for example, just watch. If I take a random matrix over F, say 10 by 10, and raise it to the power of 10, it's still tiny. Now let's say I do exactly the same thing, but with a random matrix of integers. It's not tiny. So things blow up when you work with integers. They don't blow up when you work with elements of a finite field. And this can be extremely useful in a lot of ways. But in a different direction, here's a way in which finite fields are useful in practice. So there's something called coding theory, which is used a lot for adding redundancy in a systematic way to some data. So for example, if you are burning a CD, then on the CD, it's storing a bunch of binary data, which you listen to it and it sounds like music, but it's binary data. And you want it to be the case that if you corrupt the data a little bit, you can still read it back in exactly the same way. Or you're sending a message to Mars or something, and even if it gets corrupted along the way, which is maybe likely, you can still read it correctly as long as it's not too corrupted. Obviously, if you corrupt something so much that you can't tell that it was corrupted, it's just completely different but looks valid, then you can't correct that. So the idea is what you do is well, a code is by definition a subspace of a finite dimensional vector space over a finite field. So it's just a subspace, but in the context of finite fields. So it's a special type of vector space. And the idea is you encode your message as a sequence of elements of the subspace in such a way that if you, it depends on the code, but in the one I'm about to show you, if you flip one of the bits, like if one of the bits gets corrupted, then the resulting vector goes from being in the subspace to not being in the subspace. And so you know that there was an error. And moreover, if you just take whatever you get, assuming there is at most one error, you find the element of the subspace that's closest to the vector you got, that will be the original vector. And so you can always correct one error if there's an error. So it's not just that you know there's an error, which is what you would get if you added a parity bit or something, it's that you can correct the error. So here's just a little example in Sage. If you do codes.tab, you'll see that there's a large number of predefined codes in Sage. a code, again, is just a vector space in the context of linear algebra over finite fields. And one particular example is a Hamming code, Hamming being a mathematician slash engineer who did an enormous amount of fundamental research into coding theory. And it's just the vector space that has this basis right here. So written out as a vector space, it's a vector space of dimension 4 sitting inside of a ambient 7-dimensional vector space over the finite field of cardinality 2. So the simplest possible example of a finite field is the finite field with two elements, 0 and 1. And 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 0, etc. There's 16 elements of this vector space, etc. Now here's the neat thing. So let's take a message. Let's imagine we have a message. We've encoded it as a sequence of vectors. So let's see. I want to do this from scratch. So I'm going to take one of these vectors right here. So the correct message was 1, 1, 1, and then 4 zeros. So now what I'm going to do is I'm going to change one of the bits. So somebody choose a bit to change. Which position? Okay, I'm going to change the first bit to a 0. And now I asked for decode, and look what it did. It figured out that the first bit was the one that was wrong, and it fixed it. So isn't that neat? You can imagine building magic tricks on this. But in any case, this is just the most basic example of a very general area that there's, like whole PhD theses written on and so on called coding theory. The second person who was involved in Sage development after me was a coding theorist. So we've had a lot of coding theory from the very beginning. Okay, so that's coding theory. I gave some links in the slides to some places if you want to see more about coding theory in Sage. So there's a reference manual section right here. So you can see all these different things related to coding theory. But it's pretty neat, and it's amazing the clever places in which people find subspaces of vector spaces over finite fields with good properties from the point of view of coding theory. They end up often arising from algebraic geometry and all kinds of surprisingly abstract areas of math. And people will run computations that last a very long time searching for codes with really good properties. Or they'll prove that if you want, that they'll prove something about the number of bits that you need in your vector if you want to be able to correct 2 errors. And you bound the cardinality of your base field to be at most, some number. So there's a huge number of obvious questions that kind of pop up about what are the best codes with certain properties. So I don't know, it's a really beautiful area of mathematics with a lot of good work that's been done and a lot of open problems. Okay, some remarks about asymptotically fast algorithms. So in Sage, I just showed you ridiculously tiny examples in the lecture today, but you can do computations with pretty big matrices. So I'll first show you a blatant lie. Let's use timeit to compute the determinant of this random 100 by 100 matrix. By the way, there's a matrix plot command like that, which will plot a matrix, and it normalizes the values. So I guess that matrix has a couple of values that are very large, and so all the values kind of look the same, which is really annoying. But there's that. So notice that this said it can compute the determinant in 208 nanoseconds. You should not believe that. Partly because that's really, really fast. Second, because I put lie here with 3 exclamation points. So any idea why? Oh, I guess it's pretty obvious since I put this here. So let me just explain what's going on. What it does is it computes the determinant of the matrix, and if you don't change any of the entries of the matrix and you ask for the determinant again, it just gives you back the number it already knows. Why recompute it every time? And so timeit, the way timeit works is it runs the command over and over again and then tells you the fastest times. There are a bunch of things in Sage that are like this. You should always watch out. If you get something where it appears to be ridiculously fast, it's probably really slow, but it's caching a result. Okay? It's using something like that cached method thing that you guys, the decorator that you guys did, that you're doing, right? One of you. Aren't you writing a cache? You're doing it, sorry. Somebody in the back. Okay, so there's a command clear cache in this particular case for matrices, which will clear the cache. So if we run that, what it does is it deletes all information that's cached about the matrix, then it does the calculation. So this is a valid answer. The time's a lot faster than what was in the slide, because when I was preparing the lecture, I had accidentally left a whole bunch of Mandelbrot fractal things running in some infinite loop. And there's, limit. Basically, those were all running and slowing down the machine a lot. So the timings would be a lot slower as a result, at least the wall time. And that's what time it gives you, wall time. It has nothing to do with the time on the CPU. It's the total elapsed time, like on a clock. Okay? So still, think about it. This is computing the determinant of a 100 by 100 matrix. So this matrix is really big. I don't know how to emphasize that to you. It's a 100 by 100. And it's doing it in without cheating in 38 milliseconds. So that's pretty impressive. Yes?
Is there any other way to get it to compute like the determinant correctly every time? Or just,
Wait,
like,
compute it what every time?
the determinant like without clearing the cache? Like if you just want to run the time it one,
Yep.
one iteration?
Yes, you can just use %time, which is right here.
Okay.
But the resolution isn't very good. That said, actually, watch. So there's a wall time command, which is and a CPU time command. I should show you these anyways. So let's clear the cache in a separate cell. And then so now if you do t equals wall time, what that does is it returns the number of seconds as a floating point number since the epoch, which was, the epoch is when Unix started in like 1970, and it will overflow in, I think, 2038, and there are a lot of people really terrified about this, but I'm not one of them. So that's what that does. And if you do s equals CPU time, that returns how long the process that you're running in, this Python process, has been running since starting, but not how long in terms of the clock time, but how much actual time has been scheduled on the CPU. Okay. So if it's multi-threaded, for example, this number could be pretty big. Okay, so the neat thing though is you can do print wall time of t and print CPU time of s. And what that will do, so wall time of t is just equivalent to wall time minus t. So this is the same thing as wall time minus t. It's just a little cleaner way of doing it. And this is the same thing as CPU time minus s. So those two things will print out the elapsed time on the wall to do this calculation and the elapsed CPU time to do the calculation. And the nice thing is you're controlling it completely yourself rather than using %time or %time it. So you can just throw these wall time and CPU time commands anywhere inside of code if you're trying to optimize things, and it can be useful. Okay, so now let's try it out. And you can see that it printed out two numbers, the wall time and CPU time. And they're actually a lot more useful than %time because they have better resolution. %time, I mean, it's just not very good. It says 0.04, but that's, oops, that's just, well, there's really a lot more resolution there. So remember these two commands, wall time and CPU time. So wall time really just calls, I think, time.time in the Python standard library. And I forget what, CPU time does something more clever. Okay. So let's do another one. Here's a random 200 by 200 matrix over the integers, and it computes the determinant in a half second. And the determinant is this big number. So it's not like just a floating point approximation or anything. So you can bet it's not using the formula, the very top left entry, delete, that it's not using the expansion by cofactors formula, because that would take, the number of steps would be 200 factorial. So it's using a much more clever algorithm. And just for comparison, the fastest maybe open source computer algebra system besides Sage. Well, I don't want to do Shift Enter. I tried it with Paris, and it took 61 seconds to do the same thing. And so the difference between these two, it's not that in Sage we implemented the same algorithm as in this other system more quickly. And if you were to use Mathematic, or at least last time I tried it, or some of the other systems like Maple, it would be similarly very, very slow last time I tried. But it's not that we have implemented the same algorithm. It's a fundamentally different algorithm. It's what's called an asymptotically fast algorithm, by which you think about the complexity of doing the determinant calculation. And, well, by complexity, I mean the number of steps, and you have to worry about things like bit operations versus arithmetic operations and so on. But, you know, like the naive algorithm for computing the determinant is, of course, the expansion by cofactors algorithm. I'm trying to find a pen. I'm not finding a pen. It's big. Wow. Big O of n factorial. So for that, you can only, you know, do if you use that algorithm, you can do, I don't know, determinants up to like 20 by 20 or something. I don't know how far you could go. But there are some much more clever algorithms for computing determinants. So there's an O of n cubed algorithm, which you probably all know. This is arithmetic operations, so I'm not worrying at all about how big the numbers get or how small they get, or, you know, a 100-digit number versus a 2-digit number. So does anybody know an O of n cubed algorithm to compute the determinant? You should have all learned this in 308, by the way. Which for a 3 by 3 matrix is kind of worse, but in practice. But for a big matrix, it's massively better. Anybody know? Do you know any O of n cubed? By O of n cubed, I mean if you take an n by n matrix, the number of steps is n cubed to do something. Do you know any O of n cubed algorithms related to matrices? Multiplication. That's an O of n cubed algorithm, true. At least the straightforward one. And there is, in fact, an enormous amount of work. There is a relationship between matrix multiplication and determinants, but can anybody think of any other algorithms they learned about in a linear algebra class? Row reduction, yes, that's O of n cubed. Because what do? You take the generic, if your matrix has lots of non-zero entries, more or less you take the first row, you clear the column, and each time you do that, you're doing n squared operations, because you have to add your first row to each of the other rows, and that's n operations each time, and there's n rows. So that's n squared operations, and then you do that for each of the columns. So that's big O of n cubed operations. And you can compute the determinant via computing the echelon form. All you have to do is, as you compute the reduced row echelon form, anytime you do the rescaling, you just keep track of those rescalings and multiply them all together, and that gives you the determinant, right? So remember that Gauss elimination allows you to write a matrix as a product of elementary matrices, and the determinants of all the elementary matrices are really easy. So that's why there's an O of n cubed algorithm. But even that doesn't explain, that's how you get this sort of speed. But to get that sort of speed, you have to do something completely different, which is really weird. So I think it gives a good taste, though, of of the flavor of these asymptotically fast algorithms. But just to illustrate, while I talk, I'll try a bigger one. I'm going to make it twice as big. Let's see how long this takes. So if it's an O of n cubed algorithm, then making it twice as big would mean that it takes about 8 times as long. Let's see what happens. It did not take about 8 times as long. Notice it took a lot less than 8 times as long. It took about 5 times as long. 5 being a lot less than 8. And I'm pretty sure if you tried this in Paris with 400, that's going to take a long time, but it's going to be probably about 400 or 500 seconds at least. So it gets really daunting. This is pretty neat. That's a big determinant that we're getting out. So let me tell you how it finds, it it's ridiculously funny and complicated how it gets that determinant. So here's what it does. It takes that 400 by 400 matrix, and let's just call it A. So this is really funny. Here's what it does. It chooses a random vector V, and then it says, hey, I'd like the determinant of A, so I'm going to solve AX equal to V. And then I'm going to take the solution that I found and look at the denominators in the solution vector X, and that's probably the determinant. And if it isn't the determinant, it's really close to the determinant. And so I can fix that easily. So there's a few things to be explained there, but that's the basic idea. You just solve AX equal to V for some random choice of vector V. Of course, the question is, how do you solve that? Why is solving that a good idea? By the way, the reason that if you take your vector V to have integer coefficients, then solve AX equal to V, then what you'll find is that by Cramer's rule, in fact, the denominator of X, by which I mean the least common multiple of the denominators of the elements of X, this divides the determinant of A. And with high probability, it's almost the determinant of A. Like if you divide determinant of A by this, it'll be a really, really small number, probably 1. So Cramer's rule tells you that. Cramer's rule gives a formula for X in terms of determinants of A, in terms of the determinant of A and V. And if you just look at that formula, you see that it has determinant of A in the denominator. So that's the only thing in the denominator. So it's ridiculous, but if you have some magic gadget that will solve systems like this, then you can compute determinants quickly. Of course, this is kind of a more interesting problem, solving systems over the rational numbers. And there is, in fact, a very, very fast code for solving this problem, which involves these asymptotically fast libraries. And so let me tell you a little about that code. So there's a C library called IML, Integer Matrix Library, and it's in Sage. It was written by some student at University of Waterloo whose thesis advisor, some master's student, his thesis advisor is probably the best guy in the world at exact linear algebra and asymptotically fast algorithms. But he's not necessarily the best guy in the world at coding, but his student was incredibly good at writing the C library. He wrote it, got a master's degree, went off and worked at a bank. But it's a really, really good library. And what it does is it, given this input, it will find an X. It finds an X that solves this system. And here's the crazy way it does that. So remember finite fields that come up in coding theory. So if you try to solve this directly using Gauss elimination, your matrix, your entries just get enormous. Think about it. If you try to clear the first column, you probably remember doing this in 308. You try to clear the column and the numbers just get really big and you get all these stupid denominators. Unless, of course, it's an incredibly contrived problem. But the most contrived problem, everything it blows up. Everything gets huge. But if you worked modulo a prime number, that is, just reduce everything, just change all the numbers so that they're modulo some prime p, then the numbers aren't going to get big when you do the echelon form. They all stay small. They stay clean and manageable. In fact, linear algebra class would be much more pleasant if you just worked mod 7 throughout the entire class. There would be no denominators ever. So maybe that's how linear algebra should be taught. But in any case, that's what it does. It starts by reducing mod p, and it, in fact, to be clever, it works mod several primes p at once in parallel. And it also, what it does is it solves the system mod p and mod p squared and mod p cubed for several different primes p at the same time. And it somehow plays off how many primes to use and how big of a power of p to use. And by the way, there's a clever trick that makes it so that solving mod p squared is the same as solving two systems mod p. So that's what you do. You solve mod lots of powers of p and lots of different p, and you put them all together using more or less the Chinese remainder theorem. Though in fact, there's something much more clever than the Chinese remainder theorem, which plays a key role in this, called rational reconstruction, which is a very surprising thing that comes out of the Euclidean algorithm. But what it does is, if you have a rational number mod a power of a prime, it allows you to determine that rational number subject to certain constraints very, very efficiently. In any case, it solves the system, and then the question comes, how do you solve it quickly mod p? That's what we've reduced to. And you could just do Gauss elimination mod p, but that's still big O of n cubed. So there's a big surprise here, and then a big surprise on top of the big surprise. So you want to do it, and you want it to be better than big O of n cubed. Because if it's big O of n cubed, even mod p, then it's still going to go from 0.46 to about 8 or 9 seconds, and then 64 seconds, and you're really unhappy. If I do it with 800, I bet it's going to be still manageable. So here's the next trick. You can reduce the problem of solving the system that is putting this in echelon form to matrix multiplications. And all you do is you basically divide your matrix up into a square like that, and then you do echelon of a 2 by 2 matrix. And that just involves, like, you literally think of it as a block sum of B, C, D, and E. And then you just multiply through by B inverse, and then add that one to the bottom one. And then, you just do Gauss elimination on a 2 by 2 matrix. Of course, this doesn't really work because B is an invertible, but if you permute the rows and columns appropriately, it does work, and you just undo that at the end. So it actually totally works. It's just a pain in the butt to implement and get right. And boy, is it, it's hard to do, but you can do it. So you implement it, you get it right, and then you can completely reduce the question of putting this in echelon form to matrix multiplication by this recursive decomposition. But then the problem is, how do you do matrix multiplications quickly, mod p? And there's 2 tricks that you use to do that. So you have these matrices, say, are like 200 by 200, so they're pretty big. And you want to multiply them together. You have 2 big matrices mod p that you want to multiply together. So there's 2 major and surprising tricks. One, these pins. But basically, you want to multiply these 2 matrices, so you just divide them up into little submatrices and multiply them. Oops. And it turns out that there's a guy, Strawson, who figured out how to multiply 2 by 2 matrices using 7 multiplies instead of 8, which is a very famous result. If you do this, you get an asymptotic complexity for matrix multiplication that's big O of n to the log base 2 of 7, which is less than 3, because log base 2 of 8 is 3. And that's better. And so then you have the question of how do you multiply the smaller matrices quickly? And so you could just implement so you have to figure out what the appropriate cutoff is. So you keep recursively decomposing, and it gets to be very painful if your matrix isn't, a power of 2 size. You keep recursively decomposing until you get to smaller matrices, and then you multiply those. But how do you do that efficiently? Turns out that you turn them all into floating point matrices, because GPU's hardware just turns out to be really good at multiplying matrices with floating point entries. And so at the end of the day, you start with taking your integers, you reduce them modulo many different primes, then you take it mod 1 prime, you make your matrix even smaller, you do lots of multiplies, and for the little tiny matrices at the base level, you turn them into floating point numbers, and you do the multiplies there, and you make the matrices small enough so that they don't overflow. And you take advantage of the super fast hardware for matrix multiplication with floating point numbers that exist because of video games, numerical simulations, that sort of thing. So that's how this works, and that's why this only takes 14 seconds instead of hours and hours and hours, which it would otherwise take. And is very parallelizable or parallel friendly. Okay, so that is just a little taste of asymptotically fast linear algebra. And then next time we'll start talking about either group theory or graph theory, probably graph theory. Cool.